I'm Rob Hoyt. My email is there on the screen, hoyt@tethers.com. If you've got any follow-up questions or want to talk about any of these technologies. What I'd like to talk today about is work that we've been doing recently to develop a suite of technologies to enable in-space services. So I thought I'd first talk about a little bit about the motivation behind the work, the range of technologies that we are working to implement, and then tell you about some of the technologies that we're working on, mainly focusing on the ones that are relevant to small satellite missions. So the reason that we're pursuing these is our overall motivation is that we are working to help develop a robust and sustainable in-space economy to help support mankind's expansion out into the solar system. And when you look at that, there are a number of potential markets that a variety of different commercial and government entities are pursuing to create markets in space, ranging from asteroid resources, propellant depots, space debris collection and possibly recycling, space tourism. The challenge that all of these markets have on their own is that they've got kind of a chicken and the egg problem, in that in order for a in-space business to be viable, you need both the supply side, the service provider, and the customer to kind of stand up their businesses in parallel, in unison. And getting that all coordinated is quite challenging. If a company were able to go and get a lot of asteroid resources, they still might not have a viable business if there isn't a in-space customer that is stood up and ready to accept those resources and pay for it. Now, we see in-space services as kind of the keystone to being able to tie together many of these separate markets to be able to create a viable in-space economy. But the important part is you've got to develop both the supply side and the demand side in unison so that you can have a actually functioning economy. So we've been working on a variety of technologies trying to address the range of services that will be needed to be able to make this economy function. And so there are three areas that we have been focusing on, and I wanted to know, we call them in-space services. You'll see other acronyms and terms used by NASA and DARPA and other organizations, including OSAM for on-orbit servicing, assembly, and manufacturing. And there's a new acronym, SMART, for servicing, manufacturing, assembly, refueling, and transport. And then there's in-space manufacturing, in-space assembly, and on-orbit servicing. All of these can work together. So we have been working to develop technologies to enable, focused on these three areas: in-space servicing, which would include refueling of satellites, recovery of space debris, or recovery of satellites that are experiencing problems, and repair and upgrade of spacecraft. Next stage is in-space assembly, where you might launch a space system in a number of pieces, smaller modules that could be launched on small launch vehicles, and then use a robotic system such as the RSGS spacecraft that DARPA has been pursuing, or the OSAM-1 spacecraft that NASA and Maxar are developing, to assemble those modules together to create a functioning space system. Additionally, within in-space assembly, I would include integration of upgrade payloads or new payloads onto existing space platforms. And then on the right side is in-space manufacturing, and that's kind of an extension of in-space assembly, where instead of bringing up fully fabricated and tested modules, the space systems will launch raw materials, such as rolls of carbon fiber composite feedstock, or 3D printer filament, or raw metal blocks, and use robotic systems on orbit to transform those materials into satellite components that then can be integrated to create a functional space system. Overall, for in-space assembly and in-space manufacturing, the analyses that we have done indicate that the best value proposition, the best applications to target for initial development are ones where the space systems need components where their performance scales with size. So where bigger is better. So if you can use in-space assembly or in-space manufacturing to create a antenna or a solar array or other structure that is larger than could be fit into an available launch volume using traditional deployable technologies, then the system could achieve higher performance, whether that be higher data throughput or higher resolution or higher sensitivity. Then you can get to overall better performance per cost for a space system. So that's the overall motivation for many of these technologies that we've been developing. And now I'd kind of like to run through a handful of the different technologies that we've been working on under support from small business innovation research investments by NASA, DARPA, and the DoD. So addressing the first area, in-space servicing, and then as well in-space assembly and in-space manufacturing, we are working to integrate a number of our components together to create a MakerSat scale, particularly ESPA class robotic servicing vehicle. Now, NASA and DARPA have been making substantial investments in the RSGS robotic servicer for GEO and the OSAM-1 vehicle. But those systems are quite large. They use very large, heavy robotic arms, which require a large, rather expensive spacecraft bus to carry and support them. Now, those systems will be very useful for servicing of large vehicles like geostationary communication satellites, but their size and their cost isn't really economically viable for addressing the needs of the rapidly developing SmallSat market, such as the proliferated LEO constellations that the DoD and other organizations are working to develop. So we're looking at creating a small, low-cost MakerSat class robotic servicing vehicle that will be economically viable for things like, for missions such as refueling of small satellites, as well as in-space assembly of kind of ESPA class payloads to create modular space platforms. And the Leonite system integrates a number of the technologies that I'll talk about in a few minutes, including our KRAKEN Robotic Arms, a tool changer called ARTIE, so the arm can swap out different tools, a tool to facilitate soft and hard docking, capture of client spacecraft that we call Dactylus, and a refuelable propulsion system called Hydros, which uses water as propellant. So it's very suitable for in-space refueling architectures. And then for control of these multiple robotic arms and actually coordination of multiple robotic servicers, we are developing a suite of software control methods that we call Cylon. That'll be integrated into the system as well. So this is one of the main objectives of our research and development. And as I said, the KRAKEN robotic arms are one of the key technologies. So the KRAKEN robotic arm is a very compact, lightweight robotic arm. As you can see on the upper right, it is designed to fold up and to stow into a very compact volume. So it's suitable for nanosat class spacecraft. And we're also working to integrate it into a express rack payload for the space station I'll talk about in a minute. There are a handful of robotic arms for satellites and space systems that are on the market or in development. What makes the KRAKEN arm unique is that we have built in very precise force control capabilities into the arm. In part, we've done that for applications on the space station where we have to make sure that the arm is safe to operate around humans. So we've built in capabilities for very precisely sensing the amount of force and torque that the arm is exerting and controlling that force and torque so that we can operate it in what we call an active compliance mode, which I'll explain more in a slide or two. That active compliance is also very important for facilitating in-space servicing applications, particularly for enabling a robotic servicer to interact safely with what I would call non-deterministic systems. So if, for example, you had a client spacecraft with a solar array that has not fully deployed, so it's in kind of an unknown state, or it's got a optics cover that's loose or not fully deployed. Those components may be in an unpredictable state or even a dynamic state. And if you want to use a robotic arm to capture and manipulate them, you're going to need some compliance in that system to prevent the robotic arm from further damaging the spacecraft. So this active compliance is a very important capability of the KRAKEN arm that we believe will make it very, very useful for in-space servicing applications. To enable that compliance, the joints include what we call series elastic actuators. The design of the arm is modular, so we have 3 different sizes of joints with different torque capabilities, and we can integrate a variety of number of them together to give different degrees of freedom solutions and increase or decrease the length of the segments. The baseline system, which we've been developing for the express rack payload called MANTIS, is a 7-degree of freedom arm. It has a 1-meter reach, and its flight hardware mass we expect to be about 5 kilograms, but that total mass can vary roughly 5 to 9 kilograms depending upon the configuration for different missions. As I mentioned, one of the things we're doing is working to integrate that arm into an express rack payload intended to go into the space station and hopefully eventually the Deep Space Gateway and other manned platforms. And the MANTIS payload is intended to enable teleoperation of experiments on the space station. So the idea is to offload kind of menial and repetitive tasks from the astronauts who are quite busy and can, often experimenters can wait months and months to get a few minutes of astronaut time to do something to keep their experiment running. The idea here is the robotic arm and the teleoperation capability could enable a graduate student or a researcher on the ground to manipulate experiments and equipment on the space station so that we can greatly increase the amount of scientific throughput on the station. So illustrated on the left there is the MANTIS payload and its KRAKEN arm interacting with the Astrobee free flyer. And we're working with NASA Ames Astrobee program to develop solutions to enable collaborative operations between the free flyer and the robotic arm, developing what I call the robotic consent protocol so the 2 systems can interact safely and successfully. And one of our objectives is to use this MANTIS capability to do on-orbit demonstrations of servicing and manufacture concept of operations on the ISS. So it's in an environment where it can be well observed and we can repeat experiments and really work out the fine details of these in-space servicing mission applications. So to give you a little bit more information on this active compliance capability, what's shown here is a demonstration video that we did of the KRAKEN Arm engineering model within a mock-up of an express rack system called the Fab Lab, which is a system in development by NASA's in-space manufacturing program to enable on-orbit precision manufacturing of mission-critical metal parts. So as part of this, the KRAKEN Arm would be used to retrieve metal supplies, put them into manufacturing systems such as a 3D printer or a zero-G mill, and then move that to inspection stations and into storage again. So as I mentioned, a key objective with the MANTIS development was ensuring safety of operation around astronauts. And in terrestrial co-working robots, the typical solution is if a robotic arm runs into a person or some other obstruction, the arm will just stop and lock up. But that's not an acceptable solution on the space station, because then that arm would pose an obstruction to the astronauts that might hinder their egress in an emergency. So in the MANTIS system, the active compliance of the robotic arm enables us to precisely control how much torque and force the arm applies to perform an activity. And if it runs into an obstacle where it exceeds that force, it won't exceed that force. So if, say, the arm is maneuvering a metal part from one station to another, and a crew member happens to get in its way, the arm will just fold out of the way until the astronaut is clear of the workspace, and then the arm will go back to doing what it needs to do. And as I mentioned earlier, this active compliance can be very useful in enabling safe and reliable in-space servicing activities. So for example, if your servicing spacecraft wants to capture a client spacecraft that is rotating, or there's some velocity error between the two systems, that active compliance can enable the robotic arm to capture the client spacecraft and gradually slow down its rotation or gradually absorb the relative motion, so that it doesn't rip the arm off the servicer spacecraft or damage the client spacecraft. Okay, so with this robotic arm, we certainly want it to be able to use multiple different robotic tools. So we have also been working on a compact tool change interface that we call ARTIE. And this is a hot swap tool change interface. It's designed to be androgynous, so that in addition to being a tool change interface, it can also be a mounting and power interface that could be installed onto spacecraft or inside a space station to enable the arm and other systems to plug into power and data and actually achieve some mobility moving from port to port. An important aspect of this tool change interface is that it integrates safe-to-mate detection and control facilities, so it can protect power lines until they are securely and properly attached. And this is a technology that we've been developing in conjunction with the Astrobi and the Robonaut teams at NASA. Also in the area of connectors, we have been working on a connector solution that we call AXON to enable rapid integration of payloads and even spacecraft modules together, both on the ground before launch, as well as on orbit. So the AXON connector is a electromechanical connector that supports rapid pre-launch integration of payloads onto spacecraft. Say, if for example, you have a payload that's a little late, or at the last minute you need to add a new payload to a spacecraft, this facilitates very rapid integration of that payload onto a spacecraft before launch. And then after launch, this AXON connector will enable a robotic system, such as the LEO Knight or RSGS, to basically plug in additional payloads or expansion modules onto a spacecraft. And illustrated on the lower right is the LEO Knight system integrating a payload module onto a large communication satellite. This connector also is androgynous. So either side, so you only need one type of connector on both sides of the system, and either side of the system can secure or separate the connection, which enables this connector to work even if one of the sides of the system has the payload or one satellite module has failed. The other side of the system can still release it to enable attachment of the new replacement system. The AXON connector also includes safe-to-mate sensing, and it also includes a very innovative cover mechanism that protects the connectors and any optical or other sensitive connections from the space environment until a matching connector is attached to the system. Now getting on to the area of in-space manufacturing. We've been working for a number of years on capabilities for in-space manufacturing of structures for satellites, including the trussellator system, which manufactures high-performance carbon fiber booms on orbit. As a big step towards implementing that full truss manufacturing capability, we are currently preparing for launch a demonstration payload called MakerSat, which will fly on NASA and Maxar's OSAM-1 mission, which formerly was called Restore-L. The MakerSat payload is going to demonstrate in-space manufacture of a very long carbon fiber composite boom. We're targeting getting up to about 60 feet in length of this boom. So it'll be manufactured on orbit. We're carrying up raw carbon fiber composite feedstock and processing it on orbit to make a very precise, very stiff, and thermally stable structure on orbit that in the future could be used as essentially 2x4s to construct large structures on orbit, such as backplanes for, say, a 30-meter telescope for imaging of exoplanets, or large truss structures for long baseline interferometry and other applications. So an important aspect of this payload is it integrates metrology, so we can very precisely measure the shape and straightness of this boom, as well as inline verification of the beam's structural properties. So as we're manufacturing the boom, we're going to be testing its stiffness and other structural characteristics all along the way, so that we can verify that the structures that we manufacture on orbit will have the same or predictable performance relative to structures that we manufacture on the ground with the same technologies. So the current status of this experiment is we've held the CDR, completed that, and we're on schedule to deliver flight hardware roughly a year from now, and that again will fly on the OSAM-1 mission. And so here's a quick little video of the demonstration. So the MakerSat payload will ride on the side of the OSAM-1 mission, make the boom, and then Maxar's robotic arm is actually going to detach and reattach the payload to demonstrate some simple in-space assembly maneuvers. Now, looking a little bit further out, we are working on a project funded by DARPA that is called OrbWeaver. And the objective of OrbWeaver is to demonstrate in-space manufacture and assembly of a whole high-throughput communication satellite. Additionally, it's going to demonstrate in-space recycling of space debris into a useful product. So OrbWeaver is a payload that will ride on an ESPA ring, the large metallic ring that goes in between a launch vehicle and its primary satellite payload. You can attach a number of secondary satellites or other payloads onto the ESPA ring. And normally that ESPA ring then becomes space trash that needs to be disposed of. The OrbWeaver payload is, instead of disposing of that ring, the OrbWeaver payload is actually going to chew up the metal of most of that ring and remanufacture it to fabricate hexagonal segments for a large antenna. And then it will use robotic systems to integrate that antenna with radios and other RF components, as long as a long boom created by the trusselator, to fabricate and assemble a full functional high throughput tactical SATCOM satellite that'll be able to operate in K-band and provide very high data rates for connecting to VSAT terminals on the ground. And the architecture that we've come up with this payload uses, as you'll notice on the right there, it uses the Leo Knight robotic servicer as the robotic component of the system to enable manipulation of components, to enable operation of the tool that will chew up the ESPA ring and feed the material into the manufacturing systems. And another key aspect of this architecture is that when the payload is done, the Leo Knight can separate from the SATCOM satellite that it makes and carry with it the manufacturing and recycling systems and go off and do the same mission again. So it becomes a reusable mobile antenna factory in space that can manufacture a number of large antennas on orbit. So this project is somewhat earlier stages. We've done successful proof of concept level demonstrations of all the key technical elements, and we are working on maturing these key technologies towards a flight demonstration within several years. Now, as we consider these various different in-space services, fueling of space systems, in-space assembly of space systems, and in-space manufacturing, a key element of all of these services and activities is communications for these systems. If you've got a robotic servicer or a robotic system that's assembling a larger space system, reliable high-speed data exchange between the different components of the system and the clients is as well as the communications with the controllers on the ground, is really critical to making these capabilities all work and achieving economic viability for the system. Typical space missions just use bent pipe communication systems where you really can only interact with your space vehicle during a 10 or 15-minute overflight of a ground station, or you have to use very expensive relay services such as TDRS, which are quite limited in capabilities. Excuse me. So what we've been working on is developing a very flexible mesh network solution for SmallSats that we call SwiftLink. SwiftLink is essentially an app that runs on our Swift software-defined radios. There's an example of one of them in the center bottom there. So Swift radios are quite compact. They can fit into systems as small as CubeSats, but they're quite powerful, useful for MakerSat and even larger missions. But the SwiftLink software provides a mesh networked intersatellite communications and enables data to be exchanged between multiple satellites using IP-based protocols. So it basically turns the radio into an Ethernet port in space so that your flight computer can plug into the Ethernet port on the radio and then exchange data with other satellites and other systems and operators on the ground just using IP data protocols. This is very useful for reducing the latency for data for a variety of different missions. And for servicing systems, it will enable a robotic servicing spacecraft to stay connected to operators on the ground by hopping data from satellite to satellite, so that instead of just operating during a, say, 10-minute overpass, you can operate the robotic system throughout its entire orbit. So this SwiftLink software, we've already delivered it to our first customer. It runs on our Flight Heritage Swift hardware, and it's available now, and we're actively working to increase its data throughput capabilities and number of nodes it can support. And we're looking forward to supporting a number of in-space servicing and other missions in the future. So that is the set of technologies that we've been working on that I think are most applicable to small satellite missions. Thanks very much for participating in this, and I'd be happy to take any questions that you might have.
What are the key partnerships that will be needed to drive satellite servicing and the future OSAM market development?
Well, as I said, the key thing is really getting the clients and the suppliers of the services working together and bringing up their capabilities in unison. So a in-space refueling service isn't going to be a viable business unless there are customers who are sending up satellites that are designed to be refueled or designed to be serviced. So the servicing companies need to be actively working with potential client customers early on, showing the value proposition for these services and working to integrate refueling ports or connectors or other key technologies into those client satellites, so that when the services are up and running, there's actually customers ready to use the services.
Okay, great. Any other questions? Okay, we got another one here, Rob. It says, are you expecting future platforms to have fuel ports for draining as well as refueling?
I think that's certainly possible. I know that some of the launch system providers, they often have residual fuel left over after launch that they then have to vent or otherwise dispose of. But that could be very useful and valuable for, say, a refueling operations. So ideally, those launch system providers would integrate the same kind of refueling ports that folks such as OrbitFab and other folks are working to develop and get onto client spacecraft.
All right, we have another question here from Jeff. It says, how much manufacturing is completed in-house?
For our systems, we manufacture most of it in-house. We get metal parts and electronics boards and those sort of things manufactured by contract manufacturers, but we do the integration and programming and testing and acceptance testing here in-house.
All right. Any other questions before we wrap up here?
Okay, well, again, my email is Hoyt, Hoyt @tethers.com. If you think of any questions later on or want to follow up on any of these technologies.
All right, it looks like we got one more question here, Rob, before we go. Jeff asks, do you see any obstacles now or upcoming with your contract manufacturing?
I don't see any dramatic obstacles. You know, we as a company have been doing a lot of work to implement AS9100 and other rigorous quality assurance capabilities. And certainly some of that we'll have to figure out how to integrate that into our on-orbit manufacturing. With contract manufacturing, we need to flow down those requirements and find contract manufacturers, work with contract manufacturers who can meet the requirements of those kind of quality assurance programs.
All right, great. Well, thank you all for coming. Rob gave his email there. You can also email info@tethers.com if you have any questions. We'd be happy to meet with you guys individually if you'd like. Hope you have a great rest of your SmallSat, and we look forward to hearing from you. Thanks again for coming.
Okay, thank you.